Yeah. Okay. Perfect. Okay. The unit circle is a graph of y in plane of x. So most of you guys are still writing. Okay, if you guys can just turn to a classmate and just see if you agreed or disagreed. Maybe they'll convince you otherwise.
Yes, right?
And then sine.
Yeah. Okay, you know, I part of the graph of sine. This is one.
Well, if they don't mind sine. I feel like that's something better like this, but I put sine is used to find what value whatever angle that is. Or the latest circle and kind of like all positive.
Yeah, it's kind of like that.
Yeah.
It's like theta function.
It's very complex. I was like, I'm not gonna.
All right, guys, let's see. So agree to disagree, just share whatever your group talked about. So it's empty. Aaron, I know you came in a little late. Were you able to catch anything in the conversations? Eric, you're Brian. I always do that. Sorry. Eric, agree or disagree? What did you guys say? What do you think?
I agree.
Any little explanation maybe why?
Because your sign is equal to x, and yours is just applying a regular graph, so you y equal to x, or part of x.
Okay, so you're saying the relationship this guy has with this unit circle, right?
Yeah.
Okay. Let's see, I'm gonna get a couple to share out, agree to disagree, and then just kind of tell me what you thought. Aurora. Okay. Uh-huh.
I mean, I dragged inside in the past and did not look like a circle.
Okay. All right, that's fair. So disagree because in the past, you don't remember that.
Well, I. Heard this.
Yeah. It's all good, it's all good. Okay, thank you. Esther. Oh, you're in the same group. Oh, okay, just kidding. Luna. You agreed? Okay. Is there maybe a small reason? I see points there.
If points on it, and it's all around the unit circle, which all usually ones.
Okay, all right, so you're using points. And then I think, thank you. And I think this is Logan. LS, yeah, you just put LS. I see your hand right. I'm thinking it's you. Agree to disagree.
This thing.
It's a trademark.
I agree because of the same reason she just.
With points, like you just.
What if I didn't put points, but I know from the past that all the points are contained in the unit circle.
Okay,
So, and there's an uncanny resemblance.
okay, okay.
Irrational.
All right. And then, they're not here. Okay, that's okay. That was the last one. I have Kalia, she's not here. Okay, perfect. So turn in your warm-ups. I like everything I heard.
You're gonna provide the answer?
But I did hear some disagrees and I did hear some agrees, so we gotta see which one, right? The lesson will answer it, correct, the lesson will answer it. But that's an important question. Yeah. Thank you. Okay, thank you. Ooh. Fancy purple, silver pen, I like it. All right. Okay, guys, so yes, the theme of today is one, let's answer that question. And two, we're gonna be graphing a bunch of trig functions. So let's take a look, and then we're gonna talk about the last part of class, inverse trig function. Okay. So let's take a look. So this section here is 8.2 to 8.3. Graphs of sine and cosine. And at the end, we'll do the inverses. Inverse. And inverse. Okay. So recall that we defined sine and cosine. We introduced the unit circle. Yeah, right. So we did introduce the unit circle. Dang it, hold on, that's supposed to be a 1, but my brain kept trying to draw letters. Okay, so we get the unit circle right here with radius 1. This is the x-axis, this is the y-axis. And as we've been doing this, we have a radius, squeaky, sorry, that rotates by some angle theta. And then this point on the unit circle has coordinates x and y coordinates. And we defined cosine of theta to equal the x coordinates. And we define sine of theta to equal the y coordinates. Is that cool? Everything we've been doing so far, okay? But what we're going to do today is we're going to review them and look at them more as functions. Function. Okay. So if I just focused on this guy here, okay, what is it that you're plugging in, and what is it that we're getting outputted? So if I go here, what do I need to plug in first? You need to plug in the angle to help me find what cosine will be, which will result in the x squared, right? So what we're doing is you're going to input an angle, theta in this case. You plug it in, like let's say the angle was pi over 2 or pi over 4. Then you compute its numerical value, root 2 or 1 or whatever it is, or root 2 over 2, sorry. And then you output the numerical value of the x coordinate. Okay. For sine, same thing. I input my angle theta. So same thing, I input an angle theta. Plug that in, like pi or 3 pi over 4 or whatever it'll be, and then you get a number out. So then you output a number. I'm just going to write number this time. A number of the y coordinate. Okay. Okay. So if you were going to make a t-chart, right? Let's say I was going to make a t-chart for this guy. We've usually used the input here, and you did the output here, right? When we do a t-chart, you usually put the inputs here, and you put the outputs here. So give me an example of an input that you can plug in here.
3 pi over 4.
3 pi over 4. So then you take cosine of 3 pi over 4. And you plug that 3 pi over 4 here. 3 pi over 4 is right here. So what is the x coordinate at that angle? Positive or negative? It's going to be negative root 2 over 2. Okay. I know some of you guys on the warm-up were putting tables, right? But was your table plugging in x and y's, or was your table plugging in theta and then outputting cosine of theta? Okay. This, if I plot this table, I'm referring to this function. That's my input. This is my input here, and then this would be my output, the way you guys have been doing it with previous functions, right? So this point, the one that we just drew here, corresponds to this situation right here. 3 pi over 4. But is the coordinate of this point 3 pi over 4 comma negative root 2 over 2? What would be the coordinate of this point on the unit circle? It would be, oh crap, it would be, the x is negative. So the real coordinate is this, and then positive root 2 over 2. That's the real coordinate of that. Right? Not this guy. That's not the coordinate of this point. You see that? So I need my function, if I'm graphing sine or cosine, I need my function to include the points 3 pi over 4 comma root negative root 2 over 2. So in this case, no, the unit circle is not the graph of cosine nor sine. It's just a unit circle where we define cosine to be the x coordinate on the unit circle and sine to be the y coordinate. Okay. And so that's what we're gonna explore, that misconception, a lot of misconception that the unit circle is the graph of these, but it's not. It's just related to the graphs of these. Okay. And so we're going to switch to our usual y equals f of x notation. The textbook will switch from thetas back to x's being inputs. Okay, but there's like a, by doing that, it confuses students because you're going to confuse this x coordinate with the x coordinate on the unit circle. Okay, so when we make the switch, I want you guys to be careful with the notation. Look, when I make the switch, now I'm thinking of now you're going to think of y cosine of x, and you're going to think of y sine of x. But this notation is still using these functions. So what kind of things do you plug into cosine? What do they represent? They represent angles. So to this function, I'm still plugging in angles. You're still plugging in angles, except that now instead of calling them theta with this variable, we're going to say input angles x. X now just represents an angle. Okay. And the output is still going to represent the numerical value of the x coordinate on the unit circle. Okay. It still represents the number of the x coordinate, even though it's labeled as y. That's where it's confusing. Okay. So for example, let me move this down. For example, if I plug in cosine of 3 pi over 4, x right now is 3 pi over 4, and cosine of negative 3 pi over 4 we said is negative root 2 over 2. So y would equal that. This y equaling this is really the x coordinate on the unit circle. Okay. And then similar thing with the sine function. You still input angle X. And then now this still will represent the number of the Y coordinate on the unit circle. We're just switching the type of notation that we're using to thetas, now back to our normal X input and Y output. Okay. Okay, let me stop. Questions? Okay, let's explore the graph. Before I do that, hold on. Oh, I want to show you an animation that relates what the graph of this is of these functions are going to look like with the unit circle. And I think it's that relationship that you might confuse with the warm-up, thinking that the unit circle is the graph. All right, I'll bring it back down in case you're missing some of it. Let me show you what I mean. Okay, so let me bring this down here so it doesn't bug us. Okay, so look, here's the unit circle. Let me move this here. Here's a unit circle. We're going to focus on, what am I doing for a sine? We're going to look at the Y coordinate, okay? So as I go around the unit circle at these special angles, so for example, let's say I go to pi over 6. No, let me go to pi over 3. What's sine of pi over 3? This from, ignore this picture. What's sine of pi over 3? Root 3 over 2. Put that in a calculator. What's root 3 over 2? You put it in a calculator, it's going to be 0.866. Okay. So what's happening is for sine, oh my God, there's so much here. Let me bring this down here. I came ready with my other one though. For sine, because sine is inputting angles and outputting that numerical values, right? As I rotate around the unit circle, for example, at this angle, whatever this angle is here, that's corresponding on the angle axis to that angle right there. Okay. The Y coordinate of this point is this length right here. So at this angle, the Y coordinate is this long. Okay. So if I am trying to graph the sine function at this angle, sine is representing that length of the Y coordinate. So this length is this length. As I rotate on the unit circle, what's happening to my angle as I go look at the unit circle? Is the angle getting bigger or smaller? Bigger, which is why the angle is increasing in the angle axis. Okay. As I rotate it towards pi over 2, that Y coordinate is slowly approaching the radius of the unit circle, which is 1. Right? So notice that this Y value, this output value is going to start approaching the Y value 1 as that angle approaches pi over 2. Like that. Once I'm at pi over 2, that Y coordinate is length 1. So on the graph, it should correspond to the points pi over 2, comma 1. Like that. Once I pass pi over 2, what happens to the distance of the Y coordinate? It starts to go back down, which is why this is getting smaller. Once I get to pi, sine of pi is 0. So then I'm going to be at the point pi comma 0. Now what happens to the Y coordinate? It's going to be negative, right? So this Y coordinate now is a negative value at whatever this angle is, which is corresponding to where that angle is right here with that negative value. And so as I go around the circle, when I get at 3 pi over 2, it goes all the way to -1. And then it goes back to 0 once I get to pi. And so that it just keeps doing that as I go around. But here, once I pass pi over 2, I'm supposed to be getting angles that are bigger than pi over 2, which is not showing it to me, but it will. Okay? Does that kind of sound familiar? Some of you guys? Okay. Cosine's a little more confusing. Cosine of 0 has the x coordinate, right? How long is what's the x coordinate here? 1. So now you're not looking at vertical distances, you're looking at horizontal distances because that's the x coordinate. So as I rotate my angle, look, notice that my x coordinate is going to get smaller. This length here, let me see, is there a ruler here? This is not a ruler, this is the ghetto app. Okay, so let's see. So if I measure this distance here, that's the length of that x coordinate right there, which is happening at this angle. And that, this is not correct, but that this length here is exactly this length right here. Oh, I thought that. It's kind of things I do at home when I can't find my tape measure. Let's see. So that length there should be the same as this length here. Yeah, exactly. There it is. Okay. So as I rotate around, this small x coordinate length is this small x coordinate. Once I get to pi over 2, the x coordinate is 0. So on the graph at pi over 2, I have pi over 2 comma 0. And so on. Okay. Let me go rotate one all the way around. I get to pi, the x coordinate is -1. So I should have the point pi comma -1 right here. Then the x coordinate returns back to 0. 3 pi over 2 comma 0. And then when I get to 2 pi, the x coordinate has length 1, +1. It doesn't show it, but it should be right there. Okay. So let's take a look. What you have in your notes. Let's quickly review the graph of sine. So let's see. So let's graph of sine. So you have your unit circle right here, length 1. And then on the side here, let's draw the graph. This is going to be your angle axis, angles x. And then up here, we're going to have f of x equals sine of x. You see how the whole 2 pi rotation, we split it up into fourths, pi over 2, pi, 3 pi over 2, and so on. So if this is pi over 2, I'm going to split it up into fourths. 1, 2, 3, 4. Let me do that better. Hold on. See, halfway is about here, half of that, half of that. So here's pi over 2, pi, 3 pi over 2, and then the same thing over here. 2. What? All right. So when the radius is at angle 0, what's the y? We're doing sine. So what is the y value there? 0. So if you want, you can make a little table like you guys were doing. So here's your angle x. And then here's sine of x. So you got 0, 0. So that should correspond to this point here, 0, 0. Notice that the point here is not 0, 0. Right? That's why that's this. The unit circle is not the graph. Then you get pi over 2, which is 1. So then we have the point here at 1. We have a point negative pi over 2 comma 1. And you get pi. Sine of pi is 0. So then we get that point right here. You get the angle 3 pi over 2. So far we have these ones. 3 pi over 2. The angle is going to be -1. The y-coordinate here is -1. So then you should have the point 3 pi over 2 comma -1. Put that right there. And then finally 2 pi, guys, we get 0 again. So we end up here. And so at all these different angles that we've been looking at, you have your y-coordinate correspond to this y-coordinate, 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 and then 1. So these points here, these y distances, will correspond to the smaller angles in between here, pi over 6, pi over 4, and so on. And so the graph ends up looking like this nice wave. And then if I rotate backwards, we get this similar shape. At negative pi over 2, the y-coordinate is -1. So I have negative pi over 2, -1. At negative pi, the y-coordinate is 0. At negative 3 pi over 2, the y-coordinate is 1, and so on. So you have this wave right there, and it just keeps repeating. Because the y-coordinates repeat again as you go around the circle. The y-coordinates are just going like this, up and down, up and down, up and down. And that's why your graph just keeps going up and down and up and down. All right, review vocab. Okay, you got this wave. And let's put arrows here because the graph continues this pattern. You have this wave here. The thickness of this wave, half of the thickness, there was a word for that. What was that called? Half the thickness of your wave. Amplitude. That was the amplitude. So this has an amplitude of 1. The distance, this width here is just 1 unit of width. And then your graph starts here with y-coordinate 0. It goes up, it goes down to the negatives, back to 0, and then that pattern will continue, right? What did we call that pattern? Yeah, that the period is when it does one cycle. Okay. And so this has period equal to 2 pi because it will rotate in the circle in 2 pi radians. Okay. But this wave cycles every 2 pi units. And this is because the graph of f repeats itself for 2 pi, if I plug in x plus 2 pi. Okay. Let's bring in the transformation stuff. Okay. Am I adding the 2 pi inside the parentheses or outside? Inside. So is it going to affect, is it a horizontal transformation or a vertical? Horizontal. Do I move it to the left or to the right? Remember, you do opposite. It moves to the left. So that means that if I grab this graph and I moved it 2 pi units to the left, it goes on top of itself. So it ends up with the same graph. So can you guys see that? If I grab this point here, these 2 points, and I shifted them, so here's 2 pi units to the left, it ends up looking the same over here. Okay. And so the textbook normally says a period is defined when whatever this value is, so that when you do this shift here, it ends up being right on top of itself. Okay. If I was to shift it only pi, see, the graph would end up looking something like this over here. And it doesn't land on top of itself. Okay. All right. So this is the graph of sine, not the unit circle, but there is a relationship. Okay. So let's see, let's do cosine real quick. Just to remember how to do that. And so in the homework, they're gonna give you the sign of cosine or sine, and they're gonna pick random points at the special angles. And they're gonna ask you for the coordinates of those points. So for example, let me give you one. Let's say I gave you this point here, located at 7 pi over 6. Oh, shit. 11 pi over 6. Okay. Let's say that this point right here is located at the angle 11 pi over 6. And you have to figure out the coordinates of that point. What would be the first coordinate? No, we're graphing the function, right? So what is it that you're plugging, this point here, what is the thing you're plugging in here? You're plugging in 11 pi over 6. So the first coordinate is 11 pi over 6. It's the angle. 11 pi over 6. Now to find the second coordinate, you have to figure out what sine of 11 pi over 6. Is it negative 1/2? So negative 1/2. So then you would plug in negative 1/2. So that's kind of what the homework's gonna do. They're gonna pick special points on the sine graph or the cosine graph at these special angles, and you have to write them as coordinates. Yeah. But yeah, remember, on this, the first coordinate is the angle. Okay, let's see, so graph cosine. You have a unit circle again. Similar to what we did over there. Let's do our angle x, and then f of x now is going to be cosine of x. 1. We're splitting up 2 pi into 4 pieces. 1, 2, 3, 4. 1, 2, 3, 4. 5, 3, 5, 2, 5. Negative 2, 5. Okay. So now here you're looking at the angle x and then cosine of x. So when we start at 0, what's cosine of 0? 1. So then that point 0, 1 is going to be right here. 0, 1. Then we go to pi over 2. Cosine of pi over 2? 0. So then we should have the point pi over 2, 0. So right here. And then we just write the other angles here. Cosine of pi, -1. But pi, we got the point negative, pi -1. And then the x coordinate at 3 pi over 2 is 0. So then we have the point 3 pi over 2, 0. And then finally, we go back to 2 pi. So that the x coordinate is 1. So 2 pi, 1 is right there. So we'll end up with a wave that's going to look like this. And then if you go backwards, at negative pi over 2, cosine is 0. Negative pi, cosine is -1. Sorry. Let me do it again. Negative pi over 2, what's cosine? 0. It should be here. I messed up. Sorry. And then that's negative pi, negative pi, negative 1, and then 0, and then positive. And so that wave is going to repeat. So it kind of looks like sine, except it's a little bit like of a shifted version of it. Okay. It actually starts at 0 because cosine of 0 is 1. Okay. What's the amplitude? Half the distance of this is still the same as the sine 1. The amplitude is still 1. And how long does it take for it to repeat itself? Still 2 pi. So this guy still has the same period of 2 pi. Because if I was to shift the graph 2 pi units to the left, I move it 2 pi units to the left, it ends up right on top of itself. Okay? When I used to teach this for a high school class at Cal had like this academy thing. And I would bring in spaghetti pieces. And then they would have a unit circle and they would get like the spaghetti here. Like let's say at pi over 4, the x coordinate, they would break up the spaghetti and then they would glue it on the wave here. And then you can clearly see with the spaghetti, the wave that was. I have way too many students do that. It was a small class. Okay, so what's beautiful about these functions is that when you're trying to model things in the real world with functions, because these functions oscillate and they repeat over and over and over, usually in the real world, anything that cycles or that has repetition, one of these two functions lies in there. Okay, it might look nastier, but there's usually a sine and a cosine. So examples are like the daylight, the amount of daylight throughout the year. You guys know what the summer solstice means? What does it mean? What happens in the summer solstice? When the day's the longest. What happens in the winter solstice? When the day's the shortest. Right. And then there's like the spring equinox and the autumn one. That's when the days are equal length as the night. Okay. And so that happens though every year, like that cycles, and the amount of sunlight cycles. And so that will be modeled by one of these two functions, some version of it. Okay. Your problem set is a real world problem that you guys will model using one of the, I think it was a cosine function. Okay. Anything that models repetition or cycling, these guys live in. Okay. And so the period controls how often something cycles. So the faster something cycles, think of it like sound, like a sound wave. You're doing physics. If you're doing a sound wave, it has different frequencies, right? The wave will have different frequencies. So the higher the frequency, the faster it'll cycle. And so that cycling has to do with the period. So the faster something cycles, the smaller the period is. Okay, because it cycles in short amounts of time. Let's go back with sound. You can also have like your wave be very, very long, right? You can have a really large quantity. And so the longer your wave will be, the bigger the amplitude. So there's all these little pieces, but what you guys are going to do is you're going to use your knowledge of function transformations to figure out those changes of periods and amplitudes. And so let me show you real quick what kind of things you're going to do. Dang it, I always turn up the wrong one. Oh, damn it. Do it again, huh? Sorry, the recording's going to have me teaching in the little screen, and then it's just going to share the computer screen. Forgot to unshare it. Okay, we'll do it again. I'm blinking out. What am I doing? Oh yeah, okay. Okay, so watch. Function transformation notation. You guys see it over here? All right, real quick. Is the A inside the parentheses or outside? Outside. So which coordinate will it affect? The y coordinate. Is it going to be adding or multiplying or subtracting? Adding, multiplying, right? What does that mean in transformation? What does that do to a graph when you multiply it? Right? You're going to stretch or compress vertically, right? Vertically. So right now the A is 1, and so that's why I just have the normal sine wave. So here's the points that we just plotted. But as I make A longer, it stretches it vertically. So what does that seem to affect? It seems to affect the amplitude. So yes, the y coordinate, but with the vocab we're using, it's affecting the amplitude. That's when A is bigger than 1, right? It's making it larger. But if A is less than 1, like a small decimal, it's going to compress it vertically. If the A is negative, it reflects it. So it's using everything you learned from function transformation. Okay. Let me bring it back to 1. Okay, the B. Inside or outside the function? Inside. So it's going to affect which coordinate? X. And notice that it's multiplying, right? But when you're affecting the X coordinate, you always did the opposite. So you're actually going to divide the X coordinates. So you're going to be compressing it. So if A is 2, for example, now my period was 2 pi, right? But now it divided everything by 2. It did the opposite. It divided all the X's by 2. So it actually makes the period, it divides the period by 2. So if the original period was 2 pi and I divided by 2, now the period's going to be pi. Or you can think of it from 0 to 2 pi, it'll cycle 2 times. 1, 2. Okay. If I make B equal 3, how many times will it cycle from 0 to 2 pi? 1, 2, 3. But what will be my period? 2 pi, but now you're dividing it by 3. Let's double check. 2 pi and divided by 3. Notice that 2 pi over 3 is now my new period. Okay, see that? Go back to just pi over 2. Or like that. So as I make B bigger, I'm dividing the period into smaller and smaller and smaller and smaller and smaller pieces. So it's going to be cycling a lot faster. Okay. If I go to 10, from 0, let's see, from 0 to 2 pi, it's going to cycle how many times? 10 times. So the period is 2 pi divided by 10. If I make the period, if I make the B value 1/2, let me just do 1/2. Now the period, it cycles, it's going to do 1 complete cycle in 4 pi. Because I'm dividing 2 pi by 1/2, which forces me to multiply by the reciprocal, which is 2 pi times 2, 4 pi. Okay. How many times does it cycle from 0 to 2 pi? Only half of it. Okay. So this B value tells you how to find the new period. You divide 2 pi by that B value, but it's also telling you how many times it'll cycle from 1 to 2 pi. Okay, that's what the B value will represent. Let's bring it back to 1. Okay. C. What is this guy going to do? What is that going to do to this graph? The C? It's going to shift it sideways, but in the opposite manner, right? So if I add, if C is a positive 1, what is that going to do to the graph? Shift it to the left by 1. You guys see how it's shifting it? So let me bring it back to 0. So if I shift it pi, cosine, this point, you guys see how here's cosine? The original wave went like that, but it shifted pi units to the left. Okay? So yes, it's doing the same thing that you guys learned for function transformation. It's just confusing because this cycles, okay? All right, so let me bring it back to 0. What happens when you add a number outside of the function? It's going to affect the y coordinate by either adding and moving it up or subtracting and moving it down. Same thing that you guys learned in the past, okay? 0, okay. Whoops. Sorry, my iPad turned off on me. Okay, so now let's see what happens if I make, let me get rid of these. Let's make A2. Let's make B, let's make A3. Let's make B2. C, let's make it be pi. And then D, let's make it be, I'm gonna do -1. So here's sine of x. Okay. So with your classmates, just real quick, try to describe what each of these is going to do to the original sine term, just to get an idea. And then we'll check on this, just to confirm. Try to like describe as much changes that you think are going to happen to this graph. Okay? And then determine the amplitude and the period. I know. What should the 3 do? I'm gonna stretch it so that the amplitude is now going to be 3. The 2 is going to, and we're going to do this all on the board, okay? The 2 is going to, is it going to widen the period or make it smaller? Because remember, it does the opposite. It does the opposite. Everything's inside, does the opposite. So the period is actually going to be divided by 2. Right? So what will be the new period if it's divided by 2? Pi. And then this bad boy plus pi is going to move it left by pi units, 3.14 units, and then the -1, bring it down. Let's double check. Let's see. So let's multiply this by 3. So let's see. Yep, the amplitude is 3 pi. I'm gonna put let's see, multiply by 2. Yep, the period is now pi. It cycles every pi units. And then we got plus pi. And so this one's a little hard to see, but it did shift pi units to the left. Okay. Here's the sine function, the original one, and it just moved pi units to the left. Yeah, exactly. And then we bring it down one. And then it moved everything down one like this. Okay. The hard part, before I bring it down one, let me just put it here. The hard part is going to know how to label the new axes so that now it goes in increments of pi over 4s. That's where doing it by hand gets hard, okay? Knowing what the new labeling is going to be. Okay. So when I bring this down, it was originally 1 unit above, right? So notice that the wave starts is going from here, and then here. Everything got shifted one. Okay. All right, let's do this by hand, and then we'll take a break.
You see the earthquake?
Yeah, yeah. So, okay, let's take a look. You know, we're gonna do this by hand. Let's move some of this, I have more space. Let me stop sharing, not make the same mistake I did last time. There we go. All right, guys, so let's see. So, let's see how we're gonna graph y equals 3 sine of 2x plus pi minus 1. So I'm just going to label so that you have it in your notes, everything that we just discussed. So this 3 is going to multiply y by 3. So you're going to do a stretch. The 2 does the opposite, so you're going to divide x by 2, so you have a compression. And then you guys said this shifts left by pi, shift left pi units. And then the minus 1, you go down. Okay, so what's going to be the new amplitude? New amplitude is going to be 3 because of this stretch here. That guy gives you the amplitude. And then the period, which was originally 2 pi, is going to be divided by this value 2 here that we have in front of our x. So the period becomes pi. Okay, there's different ways to approach this here, okay? One way is to draw a sine and then make all the appropriate changes. I'm going to do it a different way. I'm going to have you guys label your axes first, and then we're going to change the axes according to these transformations. Let me show you what I mean. Here's x, and then here's going to be your y. All right, so normally you're going to start with the same labeling that we have for just sine of x. Same thing. Okay. Oh, and then 1. Okay, so let's start with A here. Sorry, with our 3. What does this affect? Which coordinate? The y. So that's going to stretch everything by 3 units, right? So that means your amplitude, instead of going from -1 to 1, is now going to go from -3 to 3, before we do all the shifting, So I'm gonna multiply the y-axis by 3, everything gets tripled. So then this becomes a -3, and I multiply this by 3, so that this becomes a 3. Is that cool? So basically, this just becomes 3 to negative. Then we got to deal with the 2 here. What is that going to do to the x coordinates? It's going to divide all the x coordinates by 2. So all these bad boys, divide them by 2. So now it becomes, what's pi over 2 divided by 2? It's going to become pi over 4. So now this becomes pi over 4. I divide pi by 2, which becomes pi over 2. And then 3 pi divided by 2 means I'm multiplying it by its reciprocal, so it becomes 3 pi over 4. When I divide this by 2, it just becomes pi. And the same thing on the other side. Is that okay? So this becomes pi over 4, this becomes pi over 2, this becomes 3 pi over 4, and then this just becomes negative pi. That's before I do all the shifting. This is just basically what's gonna end up happening with my label. And then I know my sine graph was originally at this point, pi over 2, 1, and so on. So the sine graph itself will still go through those same points before I do my shifting. I'm going to do it dotted though, okay? I'm going to do it dotted. Because we have to shift that at some point. Actually, let me erase this one. That's the first way right there, right? The amplitude will be 3 units, but now the period is pi. And then what you're going to want to do, then you shift that accordingly. So all these points are going to move left by pi units. And then I'm going to bring them down by 1. So this point moves pi units to the left, but then I bring it down by 1. So it's going to end up right there. This point, pi units is 4 of these increments, right? 1, 2, 3, 4. That's pi units. So this guy is going to move 1, 2, 3, 4. Oh wait, did I mess up? Oh, I messed up this one. Sorry about that. Let's do this again. Restart. I had to shift it pi units to the left. I did pi over 2. My bad. 1, 2, 3, 4, and then down 1. Right there. This point moves pi units to the left. 1, 2, 3, 4, and then down 1. That 2 right there. Pi units to the left. 1, 2, 3, 4, down 1. Pi units to the left. 1, 2, 3, 4, down. Oh, sorry, I forgot this one. 1, 2, 3, 4, down 1. And then 1, 2, 3, 4, down. So this one will end up here. And so my final graph should be going through this wave here. And then it just keeps repeating. Okay. So I use these two stretching or compression factors to change my increments so that it models the same amplitude, the correct amplitude and the correct period. Then I'm going to graph it dotted because after that I have to shift those according to the transformation. Okay, let's just quickly confirm. This is supposed to be at the point pi -1. you don't have to label it, I'm just gonna do it for reference. This is at -3 pi/4, 2. And then so on at -2 or at -4. This is at -pi/4, negative. Bring this down just a little bit. See. See if I can do this. So we got at -pi, what did we say? -pi, -1. That's this bad boy right here. Then we got 3 pi/4, +2. That's this guy right there. And then we have -pi/4, -4. That's that guy right there. Okay. So it's matching with the coordinates that we got here. And so that way you have the right coordinates and the right units. Okay. I'll leave this here. Let's take a break. And then I'm gonna have you guys do a bunch of, because you need to practice it a couple times. If you're pretty comfortable with it, that's okay. You can I'll give you some additional questions. But yeah, let's take a break. And then I'll leave this here. So this is in general what your sine and cosine functions will look like, what the period will be, the amplitude. Is it cool if I pause this part of the video of the class since it's mainly group work? Okay. Otherwise, a video recording. We're going to move on to inverse function, which are going to be really, really useful when solving trig equations. But first, I gotta remind you guys what these guys are, especially so that you don't think they're the reciprocal ones, like secant and cosecant and all that. They're completely different things. Inverse trig function. All right. So here's a graph of the sine function. And then here's the graph of the cosine function. This won't be on the recording. Oh, it kind of is. Whoops. Are these functions one-to-one functions? Go back, we're like, oh God, what the hell did that mean?
Yeah.
Do they pass the horizontal line test? Hell no. They cross hella times, right? A lot of times. So, for example, sine of pi/2 is 1, but so is sine of -3 pi/2. So if I asked you guys, we have this function here. We know that sine of pi/2 equals 1, and sine of -3 pi/2 also equals 1. For inverse functions, I would do the opposite. I plug in a 1, but what would it output? Why that one and why not that one? Technically, from what we have, it should output both of these, right? But is that allowed for functions? No, a function can't output multiple things. It can only output one. And that's because these are not one-to-one functions. So what we need to do, this won't work here. So since our sine and cosine functions are not one-to-one, we need to what's called restrict their domains. And make them one-to-one. sorry, on the right. We gotta restrict the domain, meaning right now, the domains that we've been using are all real numbers, all the angles. We've been able to plug in any angle I want. Now, I don't want to do that. I'm gonna restrict it strategically so that it passes the horizontal line test. Okay? So most textbooks use the following restricted domains. Here. Let me go to decimals real quick. Okay, look. Here's f of x equals sine of x. Super not one-to-one. But I'm going to restrict my domain so that it does pass the horizontal line test. So you could do all kinds of restricted domain stuff. Like I can do from 0 to pi. Look, if I do from 0 to pi, does it pass the horizontal line test? Does it cross it more than once? It still fails it, right? So this restricted domain won't work. What about maybe pi over 2? Will that work? Yeah, right. But see, now I'm not capturing any of the negative values of sine. I want to capture the negative values of sine. So what can I do instead? If I restrict it from negative pi over 2 to pi over 2, now does it pass the horizontal line test? Yes, and it uses all the y values of my range from -1 to 1, right? But notice what I meant by this is, what do I mean by the textbooks use the following? Like I could have also used like 3 pi over, I could have used pi over 2 to 3 pi over 2. If I use 3 pi over 2, pi over 2, whoops. See, that still will pass the horizontal line. So there's many different restricted domains that you can choose to make it one. But the ones that textbooks usually choose is the first one, negative pi over 2 to pi over 2. That's the one they're going to use for sine, so that they only use this part of the graph to make it 1-to-1. Okay. And for cosine, they're going to do a similar thing. Let's see. So let me erase this one. Say I put cosine here. For cosine, which domain, what restriction should we make so that it captures both the positives and the negatives? What is it? Notice that if we do from 0 to pi, 0, pi, it's 1-to-1 now, and it captures all the y values in my range from -1 to 1. Okay, so those are the ones that we're going to be using to make these 1-to-1. So we're going to have y equals sine of x, but only on the interval. I'm using interval notation now. From negative pi over 2 to pi over 2. And by doing that, now I'm going to be able to have my graph only here, here, and here. So it'll look something like that. It will now be 1-to-1. It's still my sine function though. It's just only on this and on this domain. And cosine, what was the one we chose for cosine? From 0 to pi. So that one's only gonna be. 4. That one's only gonna be from here. Sure. 0 to 5 is that it? Oops. So therefore, now they are 1-to-1 on these domains, on these restricted domains. What's the range of this guy? I asked you guys function notation. What's the interval to describe the range? What are the y values going from what to what? From -1 to +1, right? What about the domain? 0, the one we chose. What's the range of this guy? Range are the y values. Still from -1 to. Okay. So then now we're gonna bring the inverse functions. So let's start with inverse sine, which is also sometimes called arc sine. Start with that one first. This is the inverse function of this guy here. So actually, let me change this to f of x. Let's change this to f of x. That way we see that the inverse of that is the inverse function sine inverse, which some textbooks also write as arc sine. Right. Which is not cosecant. Yeah, that's a reciprocal, that's different. All right, go back to the beginning of class. What kind of things were you plugging into sine? What were the inputs representing? Angles, right? And the outputs were representing the y coordinate on the unit circle. So because this is an inverse function, the inputs and outputs swap. So now, if I'm inputting angles into f, that becomes the output. So this is going to be outputs, angles. Angles are the things that you output. And the things that you're plugging in into inverse sine were the outputs of this guy. So they're going to be the inputs here represent the y coordinates on the unit circle. And so let's look at some examples. Oops, careful. Let's look at some examples of what I mean. So if I ask you what's f inverse of √2/2, I'm trying to figure out what's sine inverse of √2/2. And I'm not plugging in an angle there. I'm plugging in a particular y coordinate in the unit circle. So in the unit circle, this needs to output the angle so that this equals, so that sine of that angle equals. Okay? So this really just means I'm trying to find my angle theta, or yeah, I'll leave it like that. This means this, so that this is equivalent to saying sine of this angle better equal √2/2. Okay. Asking that question is also asking this question, but these angles can only come from this interval. That's what's important. Where theta, where theta is going to be in between negative pi over 2 and pi over 2. So yeah, because on the unit circle, I'm going to erase this in a bit, but on the unit circle, there's many angles where the y coordinate will be positive root 2 over 2. Pi over 4, 3 pi over 4, and then all the ones after that. Right? 9 pi over 4, 11 pi over 4. Like there's an infinite number of angles. But you can only choose the angles that live within this image. So what angle, and there should only be one, because this is now a one-to-one function. What angle is that? It's only pi over 4. That's the only one. 3 pi over 4 is not here. Not in this interval, outside of one. Okay. So the only one that would work here is when theta is pi over 4. So then I put all this together. So therefore, when I plug in this in your calculator, it's going to give you a weird decimal number that represents pi over 4. Okay. So go real quick on your calculator. I want you guys to know how to plug in sine inverse of root 2 over 2. It gives you what? Seven. No, yeah, that seems to be giving you this value. Oh yeah, make sure you're in I guess if you're in degree mode, it'll give you 45 degrees. If you're in radian mode, it'll give you the decimal value of pi over 4. Yeah, okay. Yeah, but what's important, guys, is basically you guys understand that the angles have to come from here, that interval. Okay, so then the graph gets a little funky. I'm going to be graphing this guy, the inverse function of this one. So now my x's and y's get swapped. So now the y coordinates are the angles, and the x coordinates are the values from like +1 to negative. Okay. You guys remember what we learned about inverse function graphs? How they have to be symmetric? How they have to be symmetric to the line y equals x? That means that my inverse function is going to be this symmetrically the same. Let's see if that's true. So here, this has coordinates negative pi over 2, negative 1. So the inverse function swaps the x's and y's. So it'll have 1 negative pi over 2. 0, 0 stays at 0, 0. And then this is pi over 2 comma 1. So now it'll be 1 comma pi over 2. Let's look at this point here. This is root 2 over 2, right? What is that? Someone help me here, decimal. Is that like 0.7-ish? Yeah? So that would be around somewhere here. And that's going to give you pi over 4. Pi over 4 is, well, it's half of this, right? Right? So that point better be right there at pi over 2 comma pi over 4. And so notice that because of the symmetry of this, the graph is actually going to go up this way and then down this way. So it's going to go something like this. Cool. Kind of, okay. So let's see what the inverse of cosine is gonna look like. This one also is called arc cosine. So cosine inverse of x, which also can be written as arc cosine of x. So it's similar. It's going to output the angles, but now x or the input values are going to represent the x coordinates on the unit circle. Okay, but what's important that you guys understand is that it outputs angles. That's what's important. Outputs angles. So let's do one real quick. Let's say I wanted to find f inverse of negative 1/2. So cosine inverse of negative 1/2. Well, this is going to have to equal an angle some angle so that cosine of that angle equals negative 1/2. Right? But that angle better live between 0 to pi. Okay? Where that angle is between 0 and pi. So on the unit circle, what angle between 0 and pi has cosine negative 1/2? 5 pi over 6. 5 pi over 6, yeah. Okay. So the one that we want is when theta is 5 pi over 6. Five pi over 6? Or 2 pi over 3. It's 2 pi over 3. Yeah, I think it's 2 pi over 3. And that, does that live between 0 and pi? 1 pi over 3, 2 pi over 3. Yes, it does. So then therefore, when I plug in negative 1/2 into inverse cosine, it's going to equal the angle 2 pi over 3. So we wanted to graph this guy. Here, the x-axis is labeled from 0 to pi. So now I have to label the y-axis from 0 to pi. And the y-axis is labeled from 1 to negative 1. So I have to label the x-axis from negative 1. For cosine, I have the point 0, 1, pi over 2, 0, and pi negative 1. So I have to swap all those coordinates for the inverse. So I would have 1, 0, pi over 2, which is right here, comma 0, and then pi negative 1 pi, which is up here. And then 2 pi over 3, just to use what we did here. 2 pi over 3 is like somewhere here. So when I plug in negative 1/2, it's going to be negative 1/2, comma 2 pi over 3. So put it like somewhere. This is hard to see, but if I reflect it across the line y equals x, it's good. this point moves kind of like over here, so the graph's moving something like this. It's a little, that one's a little hard to see. The graph's gonna look something like this. So. Okay. I'm not gonna be too picky about the graphs though, but I'm gonna be picky about this stuff. This is the important stuff you need to know, because on the calculator, you need to know how to plug that in. So from looking at the graph, what's the domain of these two functions? -1 to 1. So you want to be careful. This is the last thing I'll say. You want to be careful when you're using these inverse functions so that you don't use them incorrectly. So the domains for cosine inverse and sine inverse -1 to 1. So that means that when you do things like this, what are they right here? What's sine inverse of 2? Is 2 in the domain? No, so it's undefined. Okay, it's undefined. Cosine inverse of -5, not in the domain, it's undefined. And so you want to just be careful. Cosine and sine as functions without the restrictions, I can plug in at whatever I want to sine and cosine. But to inverse sine and inverse cosine, I can't plug in whatever I want. I have to stay within the domain of these two functions. Okay? So we're going to use these functions next week when we're solving for trig equations. So we're going to implement it. All right, guys, we're done. Oh, I did it again. Damn it. Sorry for the small screen. God, I hate